between the bases, right? Which means that the dot product looks like a delta function. Right? But in any case, we have a basis set. This is the complete basis set, our separable solution for anything, but we did solved it for a 1D well, where these solutions for the 1D well look like the following: side 1, side 2, side 3. How many people are okay with that? Okay, good. So then what we did is we went on to use that nice infinite well as a basis set to form a general solution. Right? And for the problem I did, we started out with the wave function to look like this at time equals 0. And so it's not surprising that the side 2 is the biggest component, right? Or has the highest probability of finding it. And it's not so surprising for the example that Griffiths used in the book where the initial condition was this, that instead the biggest projection was C1. What we've added today is the interpretation of that projection.
Basically what the wave looks like will determine which n, which C of n is.
Yeah. I mean, it's a projection. You know, if you have 10 in the I hat, it's going to have a big projection in the I hat, not much in anything else. Yep, and let me do it before. And so where did that interpretation of Cn squared being a probability come from? It came from this argument where we calculated the expectation. And when we calculated the expectation, it indeed looked just like the discrete probabilities. Where, for example, if you want to calculate the average grade, you take the probability of that given grade and you multiply it times that grade and you add them all up and that comes up to the average. So therefore we can interpret Cn squared as a probability. Now one thing I do want to mention is that pay particular notice to Griffiths' comment on the bottom of page 36, and I'll read it, all right? Because it pertains to what we're talking about today. Loosely speaking, Cn tells you the amount of psi n, the total wave function, that is, loosely speaking, Cn tells you the amount of psi n, the basis, that is contained in total psi. Right? Cn, loosely speaking, tells you how much of this total function is looks like that. Right? So it makes sense that this one mostly is psi 1, and it makes sense that this one is mostly psi 2.
Well, how much Cn is in the big psi?
Yeah. The Cn is telling you how much of the big psi is in that basis. Ooh, I said that okay.
Each term. I know each term.
Yeah. Okay. But here's the thing. Some people like to say that Cn squared is the probability of finding the particle in the nth stationary state. All right? That's not what I said here. It is a probability. Here's the distinction. But it is bad language. The particle is in this state. It's in a superposition state of all these. That's what the particle is. All right? But the particle is in psi, not psi n. And anyhow, in the laboratory, you don't find a particle to be in a particular state. You measure some observable, and what you get is a number.
The observable slams it into that state. Oh, that's what some of our.
Well, I don't know. Like we could take a test in the class and like have the probability of what your score is going to be, but you know, does that mean that before you graded the test and handed it back that we all have the same probability, or we're all in the same state?
I'll let you think about it more. But what it means here is that when we've solved for the wave function of this thing, it is all of these things. All right, and if we were to go and measure it, and we did find it to be in that state, maybe I'm arguing this poorly.
Well, it says at the bottom in italics that C of n squared is the probability that a measurement of the energy would yield a value of E of n.
That's right.
of
That's right.
certain energy of that level.
That's right. That's it. So really kind of have to think about this as the expectation, which is the infinite. Again, it would be like if you prepared the state 1,000,000 times, and everybody went and measured it, right? Some people might find that it had a measure of E2. Some people might find that it had E4, E5, E6, E7. But if you average them all together, you would get this number over here, the expectation value. All right? Yeah.
So, with regards just to the different N and M's and so forth,
Yeah.
is that just like a formalism? Because you know it's going to come out to 0 every time? But when N and M don't equal each other?
I don't know what you mean as a formula. It is the result of what we've done.
No, I understand that, but if you to write down the case of N not equaling M, that's always going to be 0.
Yeah.
Okay,
Does it have to do with
Yeah.
vectors and dot product?
Right.
The delta function.
So if that's always going to be 0, I mean, to go through that step, that's what I'm saying, it's like a formalism.
So our whole formalism was to do separation of variables. Why?
But all I'm saying is, like, see that?
But this is my point. Why did we do separation of variables?
To separate the variables.
To get solutions. And what's particular about those solutions?
They're square integrable solution.
Not yet.
The vector
They're a complete basis set.
basis.
Add that in, that we're looking for the Born postulate interpretation of Schrodinger's equation, which is the probabilistic interpretation, which means that these solutions that form an infinite basis set, that they have to be square normalizable. Now all of a sudden they're square normalizable and infinite basis set, so they're Hilbert, which means they have all the properties of vector spaces. So as a result of that, they have a dot product.
Right.
Therefore, all that is because of what we did.
Right, okay, so yeah, because when we're solving problems, we probably would never take the time to write an integral if N doesn't equal M, because it's 0.
No, right, exactly. And then in the end,
Yeah.
I guess this is a good jump to chapter 3, is to stop working so hard and look at more of an abstract look at this. And so, for example, instead of saying these integrals anymore, just say psi n, psi m. What does that equal to? That equals the delta function nm. So that's an abstraction of this function space, right? So what do I interpret this to mean?
And then have to be equal.
Okay, this, if you want to think back and then go over here, you would write it down as this. So this equals the integral of psi n star psi m dx. But like Mike was saying, is that as long as we know what we're doing, why write that all the time? Let's use this notation and just say, hey, we know the answer.
Right. 'cause-
So we're going to move to that. We're going to move to what I call a complex abstract vector space. Nice word, right? But what it really is, it's our vector space because we're dealing with a Hilbert space, all right? And it's complex because we have this complex number there. But it's simply an abstraction of the function space part of it. All right, so it's a lot easier to write this. And so, why write down this whole answer anymore? An abstraction of this thing is that psi general of x and t, if you want, why not just make that a ket? What's called a ket, and ket equals the sum over n of, if you want, g of t times psi n of x. All right? So, why not just use that? Because like Mike's saying, we're going to exploit all this power of our basis sets and function space being Hilbert, where things do come out to be easy. And so let's exploit that, and we'll cut down on the right. That's what you're getting.
Right, exactly.
Okay, so that's what we're going to, yeah.
I have a question. So we use this O for an operator. How would that be different? Say I was using a momentum. I wanted to calculate like a momentum for that O. I would use obviously a different operator, but how does that work?
You put in that explicit operator.
So I'd put in like whatever
Minus I, H bar, partial with respect to X.
and then just calculate with that as the operator. And
Yep. And then, like, if we're using a basis set where the eigenvalues, where the functions are eigenvalues of momentum, for example, like e to the I kx, all right, then that just pulls out a k, it just pulls out an ik out of that, right, because it's partial with respect to x. So it pulls out the eigenvalues, wherever the eigenvalues are.
So it doesn't matter what that will just give me the eigenvalues for that operator, whatever operator I put in.
If that's the case, if you're working with a basis that is an eigenbasis of that operator. So, for example, again, the e to the ikx's are a good basis set of the operator for momentum. Okay, so, I now want to move on to the next thing, and we're going to do this super quickly. All right? Well, I'm going to move through it super quickly. I'm not going to do any less details. But the point is, we're now going to do the harmonic oscillator. And again, why is the harmonic oscillator important?
Does everything without atoms.
Everything that looks like it's in stable equilibrium can be approximated as being in a harmonic oscillator potential. Right? So let's start with a harmonic oscillator potential. So let's do a harmonic oscillator. Potential, and last time we went over why it's so important. That systems near stable equilibrium can be described as being near in a harmonic oscillator potential. All right, so we write it down, maybe something like this. Here's X, and here's V of X, and again, V of X is the it's the potential energy. I got messed up there. Okay, it's the potential energy in units of joules, and it will be something like this. If you want, let's put a little particle, let's put a little electron or something like this, and this electron is in the harmonic oscillator potential. Okay, now I've left this there for a reason. Let's now go through the steps. So I'm giving you guys now a harmonic oscillator potential problem in quantum mechanics. Do it. What's the first thing you write down? You don't write down F equals ma, you write down Schrodinger's time-dependent equation. So H0 psi equals IH partial of psi with respect to t. Next, what?
Separation of variables.
Through separation of variables, I'm going to do separation of variables, and I'm going to pull out the time-dependent part, and that turns out to be the same all the time, unless the potential itself is a function of time. I do want to say, but is this potential a function of time?
No.
I mean, it's just a
No,
function,
it's just a function of X.
All right? So then I know that G of t is going to equal
Negative I E over H bar T.
yeah, done. I'm doing all the work I need to do.
Yeah.
Okay? That leaves me with having to solve what?
Small little psi.
Okay. H0, and we'll give it a name. You would say little psi, and David would say Schrodinger's time independent, both the same, right? So H little psi, all right? And then we're going to expect that they're going to be an infinite number of solutions, right? Because separable case. So this equals En psi n. Right?
Yep.
Then we've got to make sure we have to write this down. We have to solve this. So we need to solve this. We need to solve this. Solve for psi n's. Okay, but then once we solve for psi n's, what's the next step?
Solve for the CN.
Okay, that implies normalized.